Okay, problem 3.32. We're introduced to the concept of something called an anti-Hermitian or a skew Hermitian, where the Hermitian conjugate is equivalent to the negative of said anti-Hermitian. In part A, we are asked to show that the expectation value of this anti-Hermitian operator is imaginary. So by default, right, I know that my expectation value of any arbitrary operator, in this case my anti-Hermitian Q hat, is going to equal it sandwiched in between two states like this, right? Now, if I want to show that this term is imaginary, my first instinct would be to introduce complex conjugates, because we know that for inner products like this, you can switch the order around. You know, you can put the left side on the right side and the right side on the left side by introducing a complex conjugate on top of the entire thing, right? But in this case, because of the fact that this is just an inner product of a wave function with itself, this isn't really going to change anything. All it's going to do is it's going to flip our operator into its Hermitian conjugate, which in this case is going to be the negative of itself, right? So this is effectively equivalent to the inner product of this with itself, this time with the conjugate transpose. And this entire thing is being applied with a complex conjugate in front on the top, like this. So in that case, well, I know that the Hermitian conjugate is equal to the negative of itself. So this is also equal to just negative of the inner product, sandwiching Q hat again with itself, which in that case, that's just equal to the negative of the expectation value of Q complex conjugate, right? So that means that the expectation value is equivalent to the negative of its complex conjugate, which is only true if this term right here is imaginary. So there, just like that, we've proved that the expectation value of an anti-Hermitian is therefore imaginary. Okay, part B, we want to show that the eigenvalues of an anti-Hermitian operator are imaginary. So I'm just going to start off by writing out the eigenvalue equation. In which case for this, it would be that my function n, so Q hat times my function n is going to equal the corresponding eigenvalue, little q n, on that same function n, like that, right? So at this point, if I want to work with eigenvalues, if I want to somehow get an equation in terms of eigenvalues, well, I can sort of follow the same prompting that I was given in part A, right? Because part A told us that we want to work with expectation values. And assuming that, assuming that the textbook is going to be nice and it's going to sort of give us a gradual progression in the same manner of how we solved part A, maybe we want to try a derivation in the same way, where maybe I can introduce an inner product again and try to get something that looks like an expectation value, and maybe I can work in a complex conjugate, flip them around, see if I can somehow massage out of equation somewhere where I can get some sort of relation for the individual eigenvalues of Q hat. Right? So let's do that. Suppose that I just arbitrarily decided to multiply a bra on both sides on the left. So if I do, Fn with itself on the left and on the right, Fn with itself as well. Now this term is an eigenvalue, right? It's not a function. It can just come out of the inner product. And now on this side, I'm just going to, guess and check at this point with this kind of derivation. And I'm going to follow the prompting that I was given in part A, where part A sort of implied that, hey, if I'm working with imaginary values, maybe I want to try to introduce something like a complex conjugate to create a proof that involves imaginary values. So what if I just arbitrarily flip this, right? This is equivalent to the same inner product, but this time with the conjugate. And this entire thing is having a complex conjugate introduced at the front, because what I'm doing here is I'm effectively arbitrarily flipping the order of this inner product, moving the right Fn to the left and the left Fn to the right, which in the process is going to give me the transpose. In that case, since this is an anti-Hermitian, this is going to add a negative at the front. If I want to turn this back into the standard Q hat, the complex conjugate term at the front still stays. And, part B, my ultimate goal is to get some sort of equation that involves the eigenvalues only, ideally, right? Because if I want to show that the eigenvalues are imaginary, I have to create some sort of equation that gives me some sort of constraint with the eigenvalues. So ideally, I want to try and convert as many terms here into something in terms of the individual eigenvalue terms as possible, which I can do right away because I know that Q hat applied onto Fn is going to give me another Qn, right? So negative Qn, I'm going to bring it out of the complex conjugate by adding the conjugate onto it, and then the inner product of Fn with itself as a conjugate is equal to Qn Fn with itself. And at this point, well, there's nothing stopping me from arbitrarily just switching the order on this inner product again to get a matching Fn inner product with itself on the left, right? Because this is basically the same thing as just Fn inner product with itself. Since it's an inner product with itself, I can freely switch the order and add the complex conjugate at will. This is equal to, once again, Qn Fn Fn. In which case, at this point, if I moved this to the right, then what I'm going to get is 0 is equal to Qn plus Qn conjugate, all multiplied by the inner product of Fn with itself. And at this point, well, this thing is some sort of scalar quantity, right? This is a magnitude term. This is going to be some positive constant c, in which case, if this is non-zero, that must mean that Qn plus Qn star has to equal 0, in which case Qn has to equal the negative of Qn star. Therefore, since this term equals the negative of its complex conjugate, Qn is imaginary. And we've solved part B. Okay, now let's do part C. We want to show that the eigenvectors for the anti-Hermitian are orthogonal, and we are given this additional constraint that we can assume that the eigenvalues are distinct. Okay, we're going to do the same proof again, right? We're going to start off with the eigenvalue equation. So Q hat on Fn is equal to little q on that same Fn state, right? And before, right, in part B, I introduced the inner product with itself. But here, if I'm proving orthogonality, maybe I want to introduce a different eigenstate, right? So what if I did like, Fm, right? Same thing here. I'm just going to arbitrary. I'm just going to skip a step right here and drag the Qn out with Fn, right? And, the method we've been doing so far of introducing a complex conjugate at the left and flipping it hasn't failed us yet. So let's just arbitrarily decide to do that again and see if this magically gives us a formula or constraint that sort of works for us, right? So if I flip this, this becomes Fn Q transpose Fm. This entire thing now has the complex conjugate in the front. And at this point, the Q transpose can turn back into itself, but add a negative. So negative Fn Q hat Fm. And now I can flip it back again arbitrarily without any issues because I am acting in the interest of trying to get as many terms to look like each other as possible, right? I want an Fm Fn inner product so that I can match this side. So in that case, well, this let's start by getting that Q hat out as its individual eigenvalue. So this is going to be negative Qm, right? Because I'm pulling the Q hat acting on the Fm term. Fn Fm. This right side is the same. And at this point, I can just switch the order to remove the complex conjugate on top. And now I can do the same thing, right? I can move this to the right, in which case I'm going to get 0 is equal to Qn plus Qm. Oh, you know what? Quick mistake here. This complex conjugate moves out like that, so this becomes that, in which case this becomes that, right? Because the complex conjugate derives, or not doesn't, right? It distributes into the Q hat. So when I move it out of the inner product, it carries the complex conjugate with it. In which case this becomes Qn plus Qm star multiplied by the inner product of Fm with Fn. And this has to equal 0. So right away, the first thing that we notice, or the first thing that we should remember, is that this has some constraints on it. Because one, we know that eigenvalues are distinct. And two, we know that eigenvalues are imaginary. We were given statement 1 as the prompt of this question in part C, right, where we're told that we are assuming that the eigenvalues are distinct. This was proved in part B, where we wanted to show that the eigenvalues of the anti-Hermitian operator are imaginary, and we did that. So immediately for part 2, if Qn and Qm are guaranteed to be imaginary, the only way for Qn plus Qm star to equal 0 would be if Qn equals Qm, right? Because the only way for two imaginaries to add to 0 would be if one equals the negative of the other one's complex conjugate. Or sorry, if one equals, if it adding with its own complex conjugate is going to give you, I plus negative I, which is going to be equal to 0. So the only way for this term to sum to equal 0 is if the actual individual eigenvalues themselves are equivalent to each other. But we know that that's not possible because part 1, right, we were told as the start of this problem in part C that the eigenvalues have to be distinct. So that means we know that this is not possible because we know that because the eigenvalues are distinct, Qn cannot equal Qm, right? In which case, this term is not equal to 0. So if this term doesn't equal to 0, then that means this term has to equal to 0. So that must mean that the inner product of Fm with Fn, aka two arbitrary separate states for this Hermitian anti-Hermitian operator, has to equal 0, which implies orthogonality. And that's our proof for part C. Okay, part D showed that the commutator for two Hermitian operators is anti-Hermitian, and then figure out what it's like for the commutator of two anti-Hermitian operators. So let's determine, two arbitrary Hermitian operators. I'm going to call them A1 and A2. And if I'm defining their commutator, that's going to be equal to A1, A2, minus A2, A1. If I want to look at the transpose of this, then that's going to be, this entire thing transposed, but the transpose, because this is, a subtraction, the transpose goes to each individual term. So A hat 1, A hat 2 transpose minus A hat 2, A hat 1 transpose. And at this point, we are going to invoke problem 3.5, part B. So if you're not sure or you don't remember why this is a thing that's allowed, this next thing I'm going to do, please reference this video where I covered it. But this part B of problem 3.5 basically said that in the case where you have a conjugate transpose, or not a conjugate transpose, a transpose of two matrices or two operators acting on each other, you can distribute the transpose into each individual term, but in return you have to flip the order of these operators. So what I mean by that is this is actually equal to A hat 2 transpose, A hat 1 transpose. minus, and on the same way here, this order flips if I want to distribute the transpose into them. So this becomes A hat 1 transpose and A hat 2 transpose. And in that case, well, this is just equal to the negative of A hat 1 transpose, A hat 2 transpose, minus A hat 2 transpose, A hat 1 transpose, right? All I did, I pulled out the negative and I flipped the order of these two terms. And this is just equal to the negative of, because of the fact that, you know, these are Hermitian operators, they equal their transposes. This is just equal to A hat 1, A hat 2, minus A hat 2, A hat 1, which is just equal to the negative of the commutator of A hat 1, comma A hat 2. So in that case, the transpose of the commutator is equal to the negative of the commutator, which means that this is anti-Hermitian. Okay, now let's consider the case where you're dealing with two anti-Hermitian products, or not products, operators, right? So instead of A hat, let's do B hat. B hat 1, B hat 2. And I'm going to take their transpose as before. This is going to equal B hat 1, B hat 2 transpose minus B hat 2, B hat 1 transpose. Invoking the same property from problem 3.5 part B, I'm going to distribute the transposes into the individual terms by flipping the order. So this is equal to B hat 2 transpose, B hat 1 transpose, minus B hat 1 transpose, B hat 2 transpose. And hopefully you already see what's going to happen here, right? Because I can convert these back to their normal terms, right? Get rid of the transpose by adding a negative, but because there's two terms here, this is going to give a negative, this is going to give a negative, they're going to cancel out to a positive, this is going to give a negative, this is going to give a negative, they're also going to cancel out to a positive. So this is exactly the same as saying B hat 2, B hat 1, minus B hat 1, B hat 2. So if we rearrange this, this is equal to, once again, the negative of the commutator of B hat 1 and B hat 2. So it looks like regardless of if your operators are Hermitian or anti-Hermitian, the resulting commutator is always going to be anti-Hermitian, because this is also going to be therefore anti-Hermitian. And that is part D, I believe. Yeah, that's part D. So now let's move on to part E. Okay, part E, final part, show that any arbitrary operator Q hat can be written as the sum of the Hermitian operator A hat and the anti-Hermitian operator B hat. And let's give an expression for A hat and B hat in terms of the arbitrary operator and its adjoint. And I'm just realizing now that I was using my vocabulary terms wrong. This is not a transpose, it's an adjoint. Whatever, it's fine. Either way, let's write out the eigenvalue equation for Q hat, right? Because this is Q hat operating on my state is equal to Qn on that same state. Because of the fact that this is an arbitrary operator, it has an arbitrary eigenvalue, which means that we can't necessarily show if this is real or imaginary. This is just, you know, xn plus I yn. And this should immediately prompt you, because this should capture your eyes. This is a purely imaginary, right? Because this can be distributed out into xn fn plus I yn fn. So that means you have, you know, a purely real component of the eigenvalue and a purely imaginary component of the eigenvalue. We already know that for an anti-Hermitian, its corresponding eigenvalue is purely imaginary from part B, right? That should sort of prompt you and say, okay, if that's the case, maybe for a Hermitian operator, right, its supposed quote-unquote opposite, right, maybe its eigenvalue is purely real. So if we go back to the proof in part B, we can actually show this, and I'm going to do this in orange, right? This is my proof from part B. If I take this point that I've gotten, like where I'm right here in the proof, Q hat transpose is equal to Qn and then the inner product of Fn with itself like this, right? If instead of considering Q hat as the anti-Hermitian operator, what if instead I just considered it as a Hermitian operator? Well, in that case, this is just exactly the same as Q hat, right? In which case I can bring it out as its eigenvalue conjugate, right? This becomes Qn star Fn star like this, and I can get rid of the star because I can just flip the order and this remains unchanged, and this is equal to Qn Fn inner product with itself. If I then bring this over to the right like I did with the proof here on the left side over here, right, this becomes Qn minus Qn star inner product Fn with itself is equal to 0. This is a scalar. It cannot be 0. It's some positive constant, which means that Qn minus Qn star has to equal 0, which means that Qn has to equal its complex conjugate, which therefore implies that Qn is real. In the case where Q hat is a Hermitian operator. So in that case, well, what that means is that, on this same state, if I act, a hat on Fn, this gives me An, and correspondingly b hat acting on Fn gives me Bn. Well, if An is some purely imaginary number, right? If An, because this is Hermitian, if the Hermitian An gives some purely real number, right? This is real, and this is purely imaginary. I can express my Q hat as instead just the corresponding A hat and B hat, right? Because I can say that, okay, Xn can be related to An, and I can say that Iyn can be related to Bn, because An is a purely real number, Bn is a purely imaginary number. In which case, now I have, moving this back together, A hat plus B hat Fn, in which case my relation is now Q hat is equal to A hat plus B hat. Right? Now, recognize that we were told that we want to express A hat and B hat purely in terms of Q and its adjoint. So, if we're being prompted to take the adjoint, let's take the adjoint, right? Q hat adjoint is going to equal A hat adjoint plus B hat adjoint. A hat is Hermitian, so that's going to be equal to just A hat, and B hat is anti-Hermitian, it's going to add a negative minus B hat. So now we have Q hat equals A hat plus B hat, and Q hat adjoint is equal to A hat minus B hat. And now we have a system of equations. So we can just, add one equation to the other or subtract one equation to the other, and this is going to give us a new system of equation that we can actually solve for in terms of Q and Q hat, right? If we add them together, we get Q hat plus Q hat adjoint is equal to 2A hat. If we subtract them, we get Q hat minus Q hat adjoint is equal to negative, is it negative? Minus, no, 2B hat, it's just positive. Okay, there we go. And at that point, well, A hat is just equal to Q hat plus Q hat adjoint divided by 2, and B hat is equal to Q hat minus Q hat adjoint divided by 2. And with that, we have finished this problem.